So we're the Fourier Optics Lab group, and we're just going to go through the process of our lab. So basically, Fourier optics is a subfield within optics, which utilizes a system of lenses so that the optical system is able to perform a Fourier transform on light waves.
So if
So
you
there's
want,
some relevance to Fourier optics within like some other optical subfields. So like laser communications, data storage, image processing, which is what actually we're going to do specifically in our lab. And there's a lot of other fields that will also use this for like practical matters. In order to like properly understand how Fourier optics works, you need to first understand what a Fourier transform is and how Fourier analysis works. So we're going to move on to that in the next slide with the like background and theory section. So basically, Fourier transforms and Fourier analysis use this equation here, which is the equation for a Fourier transform. And we're going to be using this specifically the two-dimensional version because our objects all have x and y axis values. So the two-dimensional Fourier transform allows for like a mathematical representation of a distribution of spatial frequencies within a given function. So then next is the methods of how we actually did the experiment.
all right, so our setup is really similar to this one, where we've got our laser. We got the first mirror, which reflects the beam a little bit higher. We also use this mirror for broad adjustments, and then this one's a little bit higher, so that it's in line with the spatial filter. And this one we use for fine adjustments where we were calibrating. And we've got our spatial filter, which has got a little lens in there and a pinhole. And the lens is an incredibly small focal length, and the focal length is at the pinhole to clean the beam. Basically get rid of all high frequency nonsense. That makes the beam expand, and then we got our collimating lens, and then we've got our object, and then we've got our first lens which performs the Fourier transform at this location. And we also, whenever we do our filtering, the low pass filtering, this is where we put it at the focal point. And then we have another lens that we use to either enlarge the image or make the image smaller, just basically changing our image size with that lens. And then these were the images that we used. This is not specifically the setup on the page that we printed, but we had a whole bunch of different sized images that we used just to allow us to experiment with different sized beams. So basically just changing, the size of the beam past collimation. I think that actually we got the largest one to be fully in the beam, but the large one did help look at finer details in like the clown image.
We did have three experiments. The first one used two pinholes vertically aligned to model the Fourier transformation of those two dots, which we modeled using two direct delta functions. Then we had a rectangle aperture, which we modeled by splitting up the horizontal and vertical components. And lastly, the clown image, which is the furthest to the left. You can't really see it in this video here, but it has periodic noise in the form of diagonal lines equally spaced throughout the image. And in the Fourier plane, you're able to filter out periodic noise by blocking certain magnitudes that are displayed across the XY plane. And while we weren't necessarily able to do that, just due to the precision it involved, we were able to filter out high frequency noise, giving us a blurrier but somewhat cleaned image in our experimental procedure. To compare our experimental results with our theoretical equations, we essentially perform the same exact Fourier transform process on synthetic images. And so these images were generated to have the exact same dot spacing and rectangle proportions as the actual pinhole aperture and the actual rectangular aperture, but with no background noise and with no loss in the Fourier transform, making it a completely airtight procedure. So right away, if you go to the next slide, um, oops, we can see a comparison between the synthetic Fourier transform of the synthetic two dots at the bottom and the actual magnitude spectrum of the photographed Fourier transform of our two dots, which we experimentally apply the Fourier transform to. In the middle of the experimental one, you can see a big spike, and that's a result of the background noise causing an increase in magnitude in the center. That isn't really present in the synthetic image just because there's no additional noise. Um, Other than that, we observed a pretty good fit between both of the results. The synthetic results obviously had a very high correlation coefficient with the modeled functions, whereas the experimental data less so, albeit still to a statistically significant degree. For the rectangular Fourier transform, we can see a similar comparison between the model and the actual experimental data. Although the modeled version is more zoomed in, so you can see the peak a little bit better. We can still see those sort of decreasing intensity rectangles spreading out from the vertical and horizontal axes of the center maximum. Yeah. For experiment 3, we were unable to actually notch filter the experimental image of the clown just because, again, of the precision that it involved. And so what we instead did was use a low frequency or low band filter to filter out some of the high frequency noise. And so what that resulted in was a blurrier image, but a less noisy one, which was somewhat comparable to the procedure that we modeled synthetically, where we blocked out the the computed Fourier transform, the extra peaks that you can somewhat see in the image at the two corners of that central maximum, which blocked out most of the periodic noise in the digital clown image.
Um, so basically that was how we applied the Fourier optics techniques to like digital image transformation. And yeah.